Hi, everyone. My name is Jacob. My trend project was on reservoir computing of the spread, or reservoir computing prediction of the spread of COVID-19. So a bit of an overview of the problem. So the problem is we seek to accurately and efficiently forecast COVID-19. So this affects things like policymaking, hospital preparation, like buying PPE and all that, vaccination efforts, et cetera. And the current ensemble model used by the CDC has confident prediction horizons of about a week, which is good, but not good enough for fast preparation. So the question is, can we predict a peak well before it happens, maybe weeks? So there's two primary challenges. The challenges are non-stationary and bad, or non-stationarity and bad data. So in terms of non-stationarity, you can kind of see if we try and use past data to predict COVID, there's a lot of very flat regions. In general, the pandemic is changing. So what this plot is, this is incident cases in the US. So this is new cases per day. So if you're sick on one day, you're not counted as an incident case the next day. And this is days since the start of the pandemic, which is roughly January 22nd of 2020. So non-stationary in this case can be a result of emerging variants. So this is roughly the Omicron wave, this is roughly the Delta wave, and this is roughly kind of the midpoint between them where there was cases with both variants. That includes things, or non-stationary also includes things like individual behavior changing, like social distancing, and then also vaccination rates. So basically, if we look over here in the pandemic, in the beginning, it's a lot different. The dynamics are a lot different than later on. Top of that, there's bad data. A lot of states really, really love to underreport for some reason. Shout out to Florida. So there's these very, very noisy reportings. Part of this is a lot of states, especially towards the end of the pandemic, started reporting like once a week. And on top of that, the data, what would happen whenever a state would have a mistake in misreporting was they would report the negative of that mistake the next day. So there's a lot of very poor data. So it's difficult to use the past data to predict. So the method we did was reservoir computing. So a bit of a background on reservoir computing. So reservoir computers are a type of artificial neural network. And the overall goal is given some time series u sub t, we want to predict the next time step u sub t plus 1. So a bit of the architecture right here. So this is what's the input signal. The input signal is then fed into the reservoir. In this reservoir, we have individual neurons that are connected by a random sparsely connected graph, and each of these neurons has their own respective time series. This time series, this reservoir state is then fed into a trainable output layer, which then outputs a prediction. So in the training phase, which is roughly represented by this kind of connection right here, what happens is the input signal is fed into the reservoir. The reservoir is then output into an output layer, outputting a prediction. And then this only, most importantly, only the output layer is trained here, and the output layer is trained to recover the original input. And then the prediction phase, this connection is shut off here. The loop is closed. The output is then going to be fed back into the reservoir and then fed right back to the output, which creates predictions for a longer term. So why reservoir computing? Reservoir computing, for one, is efficient. So the training is only done on the output layer, which is very important because most of the time the training is the most computationally heavy part of machine learning. And then this is in contrast to traditional deep learning where you train multiple layers. Furthermore, reservoir computing is accurate. It's shown impressive accuracy in predicting time series very accurately, predicting some chaotic systems for multiple layout enough times. So for preprocessing, so we got to do something about this horrible data. So what we did was we filtered the data by generally the normal filtering processes, minimizing the raw filtered air. We also had to penalize large fluctuations in the filtered form, because if we didn't penalize large fluctuations, then what would happen with a normal filter is it would kind of dip up well into this noise right here, which is not what we want, because this is very clearly reporting error and not the actual dynamics of the disease. And this is, again, the same plot, incident cases, which is the new cases per day since January 22nd, 2020. This time series, we called this X sub t. The filtered form is called X sub t. And then we seek to train the reservoir computer on the interesting dynamics. So what we do is we identify the time series that are surrounding peaks in each state. And these peaks are found via a wavelet transform that is commonly used in molecular spectroscopy. And around each of those peaks, we picked 45 days in the past, 30 days in the future. The reason why we did this is because we want to be able to predict when a peak is happening, not when a peak is dying, because when a peak is dying, it's not really too important for preparation and all that. And then we did what's called detrending the data in each near peak time series, where X sub t is the filtered incident case time series, Y sub t is the time series we actually trained on. There's some reason to Z-trend. So we're trending, or eventually we're going to be training on every single state. Each state has a different total population. So you could roughly believe that the incident case time series is going to be roughly proportional to the total population. So this kind of normalizes out that effect. And then some waves are more extreme than others despite having similar dynamics. So we expect Delta and Omicron to kind of have similar enough dynamics, especially since they occurred so close to one another in terms of time. But Omicron was a lot more severe in terms of total cases. So this also kind of normalizes out that severity. So we trained a reservoir computer on all near peak detrended time series. And for comparison, we also did the same procedure by training on all the available data that wasn't around peaks. So what this plot is here, this is the incident case time series in Maryland, filtered. The black dashed line indicates the data that we picked to train on. This is the data that's surrounding peaks. So you can see right here, it kind of correctly identified Omicron, it correctly identified Delta. The goal was to try and kind of get rid of where this superposition of Omicron and Delta happens, because it's impossible to train on that because the dynamics are a superposition of two different ways. So here's some of the results, and this plot's really complicated. But so what you see here on the right is, let's say we started the forecast at time 550 days after January 22nd, 2020. What we have in this vertical axis right here is the how long that prediction was valuable. So for 550 right here, when we're training on all wave, or when we're training on only waves, what we see here is we see if we start the training at 550, or we end the training at 550, begin the forecasting at 550, we see that this prediction is ridiculously accurate. So this is like 100 days accurate, which is insane. The median case for this beginning the forecast was about 80. These error bars this was repeated 30 times. So these error bars in the interquartile range. And then we see here, it looks like the training on waves is performing a lot better. It is in this case, but in the general median case, it's predicting on an order about 20 to 30 days. The important part here is that it's training, or it's predicting in the United States data accurately for weeks. And this was also trained on state data, but there's not enough slides for that many figures. But the important thing here is that this prediction was accurate for weeks, which is amazing. So the future work is coupling what's called the susceptible, infected, recovered model with the reservoir computer to improve prediction strength. This citation is people in my research group were using knowledge-based models and coupling them with reservoir computers to make better predictions. So the normal model for disease dynamics is the SIR model, susceptible, infected, recovered. These are total populations. And we've performed fits on incident case time series around peaks. And the goal is to use this extra information, couple that with a reservoir computer, and make more accurate predictions, basically biasing our reservoir computer in a certain way. So the summary is that reservoir computing accurately forecasts COVID. This beats the model ensemble used by CDC in 538. And we expect even better predictive strength by coupling the reservoir computer with the SIR model. Acknowledgements. This work was sponsored by the following NSF award number, and special thanks to my collaborators.